The factorial of a positive integer n is written as n with an exclamation point. This is referred to as n factorial. It is defined as the product of all positive integers less than or equal to n. So, n factorial equals n times n minus 1 times n minus 2, and so on, continuing in this fashion all the way down until you get to 1. For example, 5 factorial is defined as the product of all positive integers less than or equal to 5. So we start with 5, and then multiply by every positive integer below it. 4, 3, 2, and 1. 5 times 4 times 3 times 2 times 1 is equal to 120, and so 5 factorial equals 120. By definition, 0 factorial is equal to 1. Check out the related video to kind of get an idea of where this definition comes from. Let's go ahead and explore how quickly n factorial grows for different values of n by creating a table. Here, column 1 of this table is different values of n, and the second column of this table is just their factorial value. What do we get when we multiply all the positive integers less than or equal to the value of n in the first column? What do you notice happens to n factorial as we increase our value of n? The values of n factorial grows extremely fast, even for a relatively small value of n. So where do we use factorials? One of their main uses is counting how many ways we can arrange objects. For example, if we have 3 different objects like this red, blue, and green ball, how many unique arrangements could we make with these 3 balls? Here, total arrangements refers to counting all the different lineups of the same objects, with no repeats where order matters. Changing which ball appears first, second, or third creates a new arrangement. In this particular scenario with the 3 balls, we are counting how many ways these 3 balls can fill these 3 specific positions. For example, red ball, green ball, blue ball, and red ball, blue ball, green ball are different arrangements. The green and the blue ball are in different positions between these 2 arrangements. So let's find all the unique arrangements of these 3 balls. For the first position, we could select the red, the blue, or the green ball. So there are 3 ways to choose this first ball of our 3-ball arrangement. Now consider the arrangements that start with the red ball. Knowing that the red ball is in the first position, how many different balls could we choose for the second position? We could either select the green or the blue ball. So there are 2 ways to choose the second ball in our red arrangements. This is also true for the arrangements that start with the green and the blue ball. There are 2 ways to select the second position. Regardless of which ball was selected first, there are only 2 ways to choose the second ball in each arrangement. Now, for each of these 6 arrangements shown, how many balls remain to be selected in the final position of each one? Well, 1, whichever ball hasn't been selected in the first or second position. So we had 3 choices for our first position, 2 choices for our second position, and 1 choice for our final position. The product of 3 times 2 times 1 is equal to 6. By multiplying the choices that we have for each position together, we get the total potential arrangements we can make of the unique set of 3 balls. Another way we could write this is just 3 factorial, 3 times 2 times 1, which is equal to 6. Extending this into an arbitrary set of objects, let's say we have n unique objects, we can find the total number of unique arrangements by calculating n factorial. Let's say we had 4 different balls, and we wanted to find the number of unique arrangements. Instead of brute forcing and graphing it like we did with the 3 balls, we can just use 4 factorial, which equals 4 times 3 times 2 times 1, which equals 24, to jump straight to the final answer. Anytime order matters, or we are counting structured outcomes, factorials are usually involved. If you ever take a statistics or combinatorics class, you will often run into factorials when counting how many potential outcomes or arrangements exist for different scenarios. If you found this video helpful, consider subscribing, commenting, or liking the video to support the channel. I'm Joe, and thanks for spending some time with me.